when you make radiation. So, in terms of energy, E to start equals E to the end, E to end. So, E to start is over here, was the energy of the electron in the initial shell. E to end up is the energy of the electron in the final shell. But now I have one other bit of energy. I have that in plus H nu. So in other words, H nu equals E of n initial minus E of n final. Alright, so this goes like this. E of this equals minus 13.6 EV times 1 over n initial squared minus 1 over n final squared. So this should come out to be a positive number, so that I get everything right. So this is minus 13.6 EV. So for example, we'll say like, let's go from a 2 to a 1. So 1 over 4 minus 1 over 1. So this would be an n initial equals 2 to n initial equals 1. So this is a quarter minus 1, so that's going to be a negative number.
And you got a negative.
And you've got a negative, so that comes up to positive. And so here we go.
13.6 times 3 quarters.
Right, exactly. Okay, so Bohr made these predictions. Right? And then what he did is he compared that to the spectroscopic data of hydrogen. That people had these nice formula. And they all had like 1 over n final squared minus 1 over n initial. They had no idea where all that stuff came from. He was able to reproduce all those energies, exactly get all the spectroscopic data right. So had Bohr has he taken a step towards knowing more than just classical physics? And the answer is yes. All right, and that's the Bohr model of the atom. All right, it's very important to see that. I think it's very important for every student to, with every one of their books closed, draw a hydrogen atom, do Newton's laws, write down the assumption of quantum mechanics, you know, of the quantized angular momentum, and derive Rn and En. I think that every single physics student should be able to do that because this is not too hard to do, all right? And this goes a long way in explaining to anybody at any level. That's kind of a push, but this goes a long way to explain to people at a lot of different levels the ideas of quantum mechanics, taking classical mechanics one more step, all right? And the key step was the addition of the quantized angular momentum. All right, so make sure you have this for Thursday. And again, this is experimentally verified. Bauman lines, the Lyman lines, the Paschen lines, all of those things experimentally verified. Yep.
So what should we like to have on the
This. Just this. Get Rn and En.
From the classical, right?
Yeah, the classical from Rn and En. And then once you get that, you go, hey, I just figured out the first quantum result. This is kind of called the old quantum mechanics.